We're going to be building a Pytorch embedding model. This is going to be a word embedding. This is, and I'm going to try to do it from memory. So I do have a tutorial up here. I do have a tutorial, word embeddings, encoding lexical semantics, that is going to give us the ability to create semantic similarity searches against other words. And I'm going to do that by creating our very own word embedding model. I think it's going to be neat. I'm pretty excited about it. I understand how it works. And I'm going to try to, since we're becoming Pytorch experts, we should be able to do this without using any help. I think we can do this. I think we can do it. If we need to, though, and we get stuck, we'll jump back into the tutorial. But I think we can do this on our own. So let's do this. Let's do a by model.py. So it's the main model. Import torch. And then say, what are we else? We're going to create a class. This will be our embedding. This will be torch.nn.model, I believe. Def init. This is going to pre-initialize our, we need to create this, did I type embedding? Did I type that? Yeah, okay. Embedding. Self here. We're going to be doing a word embedding model today from using Pytorch, but from scratch. So it should be pretty straightforward. I think I understand the concepts behind it. And it's only going to be for word embedding. So that way we can do semantic similarity searches. We're going to do it fully from scratch. I think we say embedding here. We got our embedding model. We need to create what our, we need a couple of linear layers. We need the embedding, which is just the same as a linear layer, but without bias. And it doesn't do a full connected mat mult. And then we need training data. All right, let's create our to-do list here. To-do list. There we go. We need to define model with linear layers. With linear layers. Spell properly here. Linear layers. And then define the model, get a data set, vectorize the data. We need to create a dictionary, word index. Okay, and then we need to enumerate our data as well. So there's a lot of tasks here. We've got, let's see here. So we need self.embedding equals torch.nn.embedding, which is just a linear layer. And we need to know two things. We need to know vocab size. And we need to know embedding dimensions, which I'll just say like, let's do 256. 256, easy. Easy. So there was this Hermes thing. Oh, we just defined our model. We need a activation, self.activation equals torch.nn. Let's do GELU. I like GELU better. GELU's my go-to. I like GELU. All right, let's see if that runs. Let's see if we made any mistakes. Typo? Did we do a typo? We're gonna find out. Yep. Embedding one. Oh, right. Let's see. So vocab, Southern wife and mama life. Thank you for subscribing. Oh, there we go. That's so amazing. Thank you for subscribing and joining the right channel for software engineering. We build AI models on this channel and we're becoming Pytorch experts. I appreciate. We are building an embedding model and from scratch, and we're going to do it without help. We're not going to look at the docs. We're not going to look at anything. We're just going to do it all from memory. And we got pretty far. So far, we've defined the model. We've got the initialization of the model, and we need to define the forward inputs. I think we can do a sentence, right? So it's just one sentence or whatever word bundle. So we got a sentence there. Okay. And then we need to push forward a bunch of words. But the thing is, we need to vectorize our words, right? Should we always do that? Yes, we should always do that in our forward. I think we're going to do that. Although, from an efficiency perspective, we could do it a little bit differently. Steven, why do you need linear layers in embedding? What are you doing there? I technically don't need them, right? I don't, technically. we're gonna see what happens when we do. We're gonna find out if it works or not. I think it's fine if we have them. Oh, you know what? See, this. We'll get to it. We'll get to it. So that's actually something I have to do. Padding. We got to do a few other things here. Number of words in our dictionary. Okay. All right. Then what do? We're only going to allow a sentence here, and then we'll figure it out. Okay. You think under Adam it would basically work out of be literally just equivalent up to noise? That's what we're going to find out. Oh yeah, we don't even know what our loss is going to be. A negative log likelihood. Negative log likelihood loss. That's what we're going to do. And then our optimizers is going to be optim will equal an array of 4 of the best. 4 of the common optimizers. So it's an RNG. We're going to try it. We're going to try all the things that we learned. That's what we're going to do. So adding linear ends up just being slightly slower for no gain. Oh, really? That's a good point. That's a good point. So then if we don't really need a linear layer, why don't we just do this? Let's just do 1 linear layer then. Okay. It won't prevent it from working. It just is wasted compute is what you're saying. Casted gradient descent. All right, we're gonna add that one as well. There we go. We got all 4. SGD. We got them all right there. Ronnie, thank you. So we get SGD, Muon, Adam, and AdamW. Got all of them together. Okay. So self.embedding. Wait, before we do that, we need to vectorize it. So def, how are we gonna do this? We need the dictionary. So this is one of our to-do items. We also need a data set. We need to vectorize the data. So we need to create dictionary. And then I think that's it, because embedding will automatically take your index number and one-hot it for you automatically. I'm pretty sure. Because it's the same. It's an embedding layer is a linear layer without bias, automatically takes your input features as a one-hot, not as a one-hot, but as a bunch of token IDs. And these are just IDs for words. That's it. So something simple. So you have like, the dog ran up the hill. Something like that. And then you tokenize that. So you have 1, 2, 3, 4, 2, 1, and 5. So those are the numbers associated with your dictionary, right? Ran up the hill. Yeah. So we vectorize it, creating features from the words, and then we have to plus padding. So we do plus zeros for padding. There you go. So we have to figure this part out here. We need to build the dictionary right here. Got to take care of this. And I want to do it here. So I think the answer would be not number of words. Let's do actual words. So all words. We need all the words. How about training set? But the thing is, you're not supposed to do it. It's like it's an anti-pattern. It's an anti-pattern. Okay. We have to do things proper, you guys. We got to do them proper. We have to put the build dictionary outside. We have to put it here. We don't have a choice. We don't have, I want it to be different. I want it to be inside my embedding class. But we have to put it outside of it, you guys. Sparse matrices are fake news. I thought so. Now that we have kind of our scaffold, what we need to do is actually build the dictionary. So I need to normalize. We need to normalize. It would also be nice if we had that method above. So we need to build the dictionary, and then we also need to normalize. Def normalize. Words. So let's see here. Maybe we can turn them into return words dot to lower dot split. And then we need to eliminate all of these symbols. So non-alphanumeric. Replace. Oh wait, before we split. There we go. All right, before we split, we need to do a regex, and it's going to be anything that we find that is a non-alphanumeric. We'll do 0 to 9, which is basically \W, right? \W plus. Oh wait. Or wait. Because we need to keep the spaces. There we go. Plus. We replace it with nothing. Okay. Let's try this. All right, let's do print normalize words. Let's make sure we got it proper. We got to make sure we got it proper, you guys. Steven, this is kind of overkill unless you add positional encoding. Like if you were adding cosine positioning embeddings and run linear, that makes sense. So Neva, this is actually kind of the plan. I want to build an embedding model and then a transformer. That's the plan. It's essentially a lookup table. While it might sound like a complex neural network, its internal mechanisms are quite straightforward and efficient. Instead of performing heavy matrix multiplications, it treats input integers as indices to grab specific rows from a weight matrix. Okay, so it is a matrix. Okay. Number of embeddings and embedding dimensions, right? So the vocab size, right? Your dictionary, how many unique items you have. We know that part, we're good. The size of the vector, that's gonna be representing each item. Oh, so what's our output gonna look like? Interesting. The most efficient way to write it is a mem copy. Really? We're gonna learn about that. When you create the layer, Pytorch initializes the matrix. So there is a matrix, usually at random numbers. Okay, so we have RNG, a matrix, a 2D, like a normal standard linear layer. It's got the same number. It's got the same format there. Okay. When you pass in an integer, the index of a word for apple, like the number 1, apple is the index number 1. The layer doesn't do math. It simply retrieves the row at that index. Really? No way! It simply retrieves the row at that index. That's all it does? Efficiency. This is computationally much cheaper. Yeah, it is! Than using a one-hot encoding followed by a linear layer. Even though the mathematical result is the exact same. I get it now. I understand. So you create a simple matrix, right, which is a 2D array. Inside that 2D array, you pass in, or you don't need a one hot so much. Well, you do. No, you don't. You just need to capture that row, right, at that index. So if the word apple, you just return row 10. Wow. Instead of doing a bunch of multiplications, you're just reading the matrix and writing directly to the place of the output instead of doing a multiplication by 1. Well, then how? Also, that indexing is the right way to view it. It's just already perfect answer. Well, then how are we going to train the embedding? So when we're creating, say we have a whole bunch of words, like a bunch of sentences and things, and it's going to identify. We need to train it. So I need to figure out how that's going to work, because back propagation is going to return, and then we need to be able to establish relationships between words based on the meaning of the position of the word in the sentence, or to give the meaning. See, that's what I want to do. I want to just train an embedding model directly, and I've got some ideas on how to do that. There's 2 approaches, because I read that in the tutorial. Thank you for the hundreds. Kyle, we're going to watch this. So here is where's our tutorial at here? Word embedding. There's 2 ways to train. And I want to do this. See, I want to be able to say, identify meaning, like likes coffee or can run, majored in physics, right? I want to extract those meanings. So there's a couple of ways to do it. Ignore the code. We didn't see it. There's an n-gram, and then we can train the model on an n-gram. Or there's a continuous bag of words. And there's there's a placeholder here. It's like, create your model to train blah, blah, blah. Like it didn't define anything. So I want to try this. That's what we're going to do. You could do like a clip, at least probably probability distribution or something. Basically, embedding layers are somewhat meaningless without a transformer. So I want like to make an embedding model just for embedding, because you can do some semantic similarity, and I want to be able to pass a bunch of data through it. And we're going to test it out because I can prove that it works. If I put in words that are similar to each other and they get a high similarity score, layers in an embedding is meaningless. Okay. So I don't know how we're going to train this. We're going to try. We're going to see what happens. Any sort of layer after an embedding basically needs some sort of new information. Got it. Yeah, I actually understand it. I get that now. I do. It's just not going to be able to have much of a representation of an understanding between the words, right? On the output. So how is it gonna perform differently? We're gonna test your idea, Neva. We're gonna test it. We're gonna test it. We're gonna try it both ways, and we're gonna see what the outcomes are. We're gonna try it both ways. We're gonna see what the results are. Definitely going to the dot product gives you a bit of info. It's dot products. All right, some matrix multiplications there. It basically counts words. Oh, what if you have a lot of words in between? So you have a whole bunch of words, but then you have a few words, and you want to see how similar those two sentences are, right? Two sentences. So there's that problem as well that we got to deal with. All right, normalize. This will almost fully normalize. So I need to lower, replace, and then I don't want to split yet. I don't think we need to split yet. This is just normalization. And then we need to vectorize, which is going to take the sentence and dictionary. But then we need to pass in the words here to build the dictionary. Right? Words, normalize, and then vectorize. But we also, do we need a vector? No, this is just post dictionary. So there we go. La la la. All right, so build dictionary. So we need to say for word in words. Let's do sentence here. Wait, let's see. All data. This is the full data. But we need to normalize this. Normalize. Normalize all the words, and then should we split them here or split them? I'll leave it there for now. Then we need to say dictionary. Note that you are replacing the words. Am I? Oh, you're right! Here, dictionary. All right, so if word in dictionary. I love liberty justice. Thank you for the 100. Thank you for the high five. Appreciate it. That was really nice for you to do there. My gratitude to you. I love liberty justice. Thank you so much. No. For word in, if word in dictionary. Thank you for the 100. Got the high five there, you guys. Appreciate it. You barely even remember working on LSTM frequently a long time ago. Did you really? Kyle, that's amazing. Let's see, if word in dictionary. La la la. Yes. Then, okay, not. Not word in dictionary, then dictionary dot update word colon len dictionary. I think we do that. Return the build dictionary. It's going to give us number of words and dictionary. So we need to say our way here. So I want, where are we here? We're going to see if we can train this model with very, very challenging set of constraints. All right, so I know we got our dictionary. That looks good. We need to update the dictionary first. with 0. It's called pad. Do the pad. This will be 0. So we start off with 0. Basically, you need to double check how Pytorch scale their embedding layers, but there may be like a square root of n either direction to make it actually normal. Okay. Okay. So we'll see. We'll see what the outputs are. All right, pad 0. All right, looks good. All right, now we've got our dictionary, all nice and sassy there. Very happy, very happy. You're requesting 500,000 units, so 5 times more. All right. All right, Loons, sounds good to me. Struggling, yeah, Steven's advice. Struggling with depression? Have you tried Breaking Bad? The dark side, your villain arc? That will cure it. It'll cure it right now. It'll work. It'll work. It'll work. I promise. Success guaranteed. I promise. Okay, I want to... We did the normalization. Did we get any... Yeah, all the words and numbers. Oh, no, we've got a problem. I see the problem. Right here. There's a bug in it. There's a bug right here. See, the bug has a bug. The bug has a bug. It's got a comma. Right there. There's a problem right there. Do we need to... I thought this would work. Do we need to say G? I don't think that... That's Perl. That's Perl's world. I think that's going to be a problem. So... Not a word. Not space. What if we did A to Z and 0 to 9? Let's try that. That worked. No, that didn't work. Because we still have periods. We still have... See if we can write one more function. And then I want to vectorize. Let's see if we can vectorize. So let's do this. So we need to say for normalize. For word in normalize. Let's return a vector. Let's say... Wait. Maybe we should return tensor? What do you think we should do here? I think maybe a tensor would be fine. Torch.tensor... Wait, torch.zeros. Z-E-R-O-S. Zeros. And then we need to do the length of the sentence. We need to have max context. Let's see, for every... Oh, no, wait. So for every word, I forgot. So we don't want to do this. We don't care about this. We don't care. Because I'm doing things that are extra that I don't need to do. I don't need to do this. So this is our words, and then I need to return for... So this will be a return the output. See, tokens. I like this better. Let's do tokens. We'll return tokens. And I want to say the ID for ID in... Or word. For word, here we go. Word in the norms. Yes. And then I look it up in the dictionary. Dictionary. There we go. That's it, right there. Done. Easy. Vectorization complete. Gotta head out, watch this tonight. Have fun. Sounds good, Catholics. Good to have you here. Thanks for dropping on in. All right. Let's test this really quick. Okay, let's test it. Let's do our... So we got our dictionary, number of words. We got our words. The number of words. And then I want to test a vect. Vect test. Equals vectorize. Words. Print. Or vec. Let's try it. Loons, I'll try to add Twitch support for ClaudeTube 404, but in another life. It'll be in another life. All right, sounds good. All right. Vectorize is not defined. Did I type it wrong? Vectorize. Steven spelling issues, you guys. Steven spelling issues. What kind of coding language is this? It looks very formal. Hey, I was going there. Trade 01. Good to have you here. One argument, dictionary. Dictionary. And we are building an embedding model. This is a precursor to transformer. An embedding model will allow us to compare two sentences and find how similar they are to each other. So you can use it for things like classification, NLP, a whole bunch of different things. A whole bunch of different things. You get a lot of use out of embedding models. Everyone's like kind of sleeping on embedding models. Did we get our vector? Python model. There we go, you guys, right there. Easy. All right, so we got our vectors. Okay. But just an embedding is not possible. Just the embedding is not possible. And embeddings are completely tied to their model, barring some interesting papers or on translations. So even trying to Vim command to our embedding model here, where we did a lot of the data manipulation, data vectorization. What's up? Watching? Oh, Oxnell, good to see you. Watching while my car getting washed. Oh, hey, we're right about to wrap up here. See, it was fun. Came late. I know you came in late. Don't worry. We'll be back tomorrow. We'll be back tomorrow, and we'll continue on our word embedding. We're going to train it. We're going to make this. We're going to make it work. We're going to do an n-gram bag of words, and we'll see how it works.